Okay, alrighty. Okay, good afternoon again, and this is Xiao, and I'm going to talk about operations and planning for connected autonomous vehicles, and just to talk about my research on this line in these few years, and share with all of you about my thoughts on this topic. So next slide, and you can, if you may, please place with video. Yeah, I just want to start with some real-world observations, and this is, this is a stop-go phenomenon that probably everyone experiences in their morning or afternoon commute. On freeways, so vehicles basically, when traffic are slightly congested, vehicles are engaged in repeated stop, acceleration, deceleration movement, or even stop and go, which is pretty bothering to all of us. Turning this off. The next slide. Okay. All right. And then you may wonder what happens to arterials with signalized intersections. Let's see whether this goes, the video. Okay, I don't know. Yeah, here. So this is a simulation about how vehicles move in front of a traffic signal light. You can see due to the alternating red and the green lights along the timeline, vehicles have to stop and go, which form this kind of stop and go waves in front of the signal intersection. So, this is also an adversary to our driving experience. So next slide. Whether on freeway or highway, this kind of annoying phenomena in human-driven traffic, that's what we have now, have lots of adverse impacts, such as congestion. You know that the congestion is pretty severe in every major city, costs a lot of money. And next, due to the excessive travel time and increased the stop and go movements, so the fuel consumptions and emissions are significantly increased, not only in the U.S. but also across the world. And following this, the safety hazards are much much more exacerbated. We know if vehicles are frequently decelerating and accelerating, the safety risks are going to soar. So how to address these problems? How to address these problems, actually? I mean, there is many ways, and this is probably the central problem that the transportation engineers should focus on. And my approach is to think of emerging technologies such as connected and autonomous vehicles. Basically, connected vehicle technology is just information sharing. So vehicles can talk to each other and to neighbor vehicles and infrastructure units. So they know each other's information. That's a connected vehicle. And then what automated vehicles, or sometimes autonomous vehicles, basically replace human drivers with robot drivers. And then, just like this video shows, actually, humans can be all turned into passengers, and the computers will take the chauffeur's job. Next slide. So why do I resort to CAV technologies for the final cure? Because with the CAV technology, we can actually control each vehicle's movement exactly and precisely. And then we can coordinate their movements in ways that we could not do with human-driven vehicles. And some fundamentals of highway traffic operations may be revolutionized due to these new technologies. Such as the past, we're going to design all these management schemes and plan the infrastructure just to accommodate the human drivers and their behaviors. But in the future, it's all about design the protocols and the programs of robot drivers. So this nice transition gives us lots of opportunities to address and resolve some of the outstanding transportation issues I mentioned earlier. So let's just talk about a couple of points about the implications of this technology for planning and operations. On planning, actually, you probably seen lots of studies and presentations here and there and talking about how CAV can boost the capacities. So if you see these two figures on the bottom, left one is actually a typical human-driven traffic fundamental diagram, basically traffic throughput over the density, and it's just like around 2,000 vehicles per lane per hour. But people claim that with CAVs and the headways can be much reduced, and the capacity can much increase or even multiply. So actually, how to realize it and how I cannot do a poll, but I am pretty curious about how many of you think that, or how's your view about how much capacity can CAV improve? Lots of uncertainties. But this is definitely something we want to work on, and we hope, and I hope, sometimes we can achieve like 5,000, 6,000 the capacity per lane. Yeah, and then, so we talk about the operations issues and planning issues about the CAV before. So how do we really use the CAV technologies to really realize these nice visions from the engineering point of view? So I think I take a three-step approach. First, I really want to look into each individual vehicle's movements and microscopic behavior, and we want to look into how to control each individual vehicle's trajectories in order to improve traffic smoothness and reduce headway. And this microscopic level of benefit will turn into macroscopic capacity improvement, and we want to understand the relationships between CAV traffic characteristics such as CAV penetration ratio and other things, and the macroscopic measures such as traffic throughput that are concerned in transportation planning. And with both of them being investigated, and then we really want to validate and test some of these hypotheses and conjectures with field experiments and data analysis. So today I'm going to go through some of my research along this line. So let's just look at the CAV-based traffic operations, mainly on the trajectory level control issues. So, I think that one major benefit of CAVs is actually we can control the vehicle trajectories, design the vehicle trajectories, and break the traditional box of car following behavior or kind of traditional driving behavior, and really design a new regime of vehicle trajectories. So for example, in the signalized intersection example, the left figure shows the traditional human-driven vehicle trajectories over a segment leading to a signal light over the time. We show the trajectories, and we've already explained stop and go waves due to the stops at the signal light. But actually with CAV traffic, with CAV technologies, we may be able to really smooth all these trajectories, let the vehicles really gently slow down during the course of running on this segment rather than being stopped right in front of them intersection. This is going to bring lots of benefit, like improving throughput because of reduced lost time and then smoother ways of passing the intersection. And of course, these trajectories are smoother, which means that the fuel consumptions are less and the safety hazards will be much mitigated. So, actually, I just want to give you a little bit flavor about our technical work on this area. So, just to give you some hints about how we can approach this kind of problem. How do we really implement that kind of smooth trajectory? So, basically, let's consider, we started from simple problem with one lane and single lane highway, and we consider fix the signal timing with green time being G, red time being R, and with advanced information technologies, we know when each vehicle arrives at which speed along this segment for some kind of a prediction horizon, like a couple of minutes or so. And then we know some physical bounds of the trajectories. Let's say there is some speed limit, and accelerations should be limited within certain range. And we only allow these vehicles to exit this segment at the green time, right? Of course, the red time bad, and red time prohibits vehicles from passing, right? And then next, we have to pay attention to the safety between every two consecutive vehicles. So we just say each vehicle cannot is sort of separated from the preceding vehicle by a certain time separation, like reaction time, and the spacing separation, like this as here shows. That means the vehicle's a length plus a safety buffer also. So basically, we want to separate all these trajectories within certain safe and comfort buffer. With these constraints and settings, what are the objectives for the trajectory control? So first is we want to reduce the travel time, right? The travel time for trajectories is very easy to calculate. It's going to be the and it's actually, you're going to look at the differences between these two time points. The time point when this vehicle arriving at the intersection, at this segment, and the time point on the top, departing from this intersection, right? And next, we want to minimize the fuel consumption. The fuel consumption can be calculated based on trajectory shape. There is many ways of doing this, but the basics is like smoother the trajectories are, lower the fuel consumption is. And we also can use some surrogate measures to describe the safety, for example, using something related to time to collision for those you know. So with these objectives and the problem settings, we can basically formulate this problem into a kind of trajectory optimization. So don't worry, actually, and I don't intend to go to the depths of the math, but I just want to show the complexity of this problem. Originally, it's kind of like an infinite. The decision variables has infinite dimensions, and objectives, including the travel delay, fuel consumption, safety, have high nonlinearity, and you have differential equations, non-convexity, and vehicle interactions. So basically, I just want to throw out these bombers to let you know this problem is really difficult. But so our contribution is actually, to develop a really simple algorithm and approach to solve this problem. So basically, the idea is if you can look at this map, and we're going to break the vehicle trajectories into a few elliptical segments, and we don't need to control every point of it, but we control some critical points, and then that's going to determine the overall shape of those trajectories, and that's going to much simplify this problem. And with this, we will be able to obtain a solution really fast, and that's going to satisfy the real-time applications, because lots of these trajectory controls have to be implemented in near real time. So we cannot afford to deal with so complex problems. So our innovations in largely reducing the complexity, and still the resulted trajectories are near optimal, very good quality. It can be just solved very fast. Next slide. So we actually compared our smooth trajectory with the benchmark with the benchmark traffic. Benchmark traffic is from the human-driven traffic, actually. So we see actually that trajectories produced from our algorithm with CAV technologies have improved all performance measures significantly. Delta T is actually improvement of the travel delay. Delta E is improvement of the fuel consumption or energy. And delta S is improvement of the safety surrogate measures. And delta M is like overall improvement, combining all these three objectives. And the solution times are just on the order of less than 10 seconds or a little bit more than that, which actually suffices for applications with a planning horizon about a couple minutes. So we have summarized some of these developments in some published and ongoing papers if you're interested. Then, and next, the first work just investigated pure CAV operations. That was probably the most ideal scenario where every vehicle is controllable and we don't need to worry about human behavior. But it was necessary to investigate that pure CAV traffic because we want to know at the best how much we can do, right? At the most optimistic scenario, how much we can do. That's going to be the future benchmark. But we have to pay attention to the transition from the pure human traffic, the human-driven vehicles, to the pure CAVs. That is mixed traffic, right? We also extended this work to include the mixed traffic conditions. And in this study, actually, we only have a percentage of vehicles as these pink trajectories show in these three figures as CAVs. And the remaining black trajectories are actually those from human-driven vehicles. So we actually use this same principle, a similar principle to optimize the vehicle trajectories. And interestingly, we found that we don't need to have an exceptionally high CAV penetration rate to achieve a good benefit or improvement from this kind of trajectory smoothing. So you see the left figure is actually 0 CAV penetration rate. So of course you can do nothing. That's actually benchmark human-driven traffic. The middle figure is actually a very few percentage penetration rate. But now you can see significant improvement. That thing is actually, whenever one CAV slows down and smooths its own trajectory, it's going to force the following vehicles, whether CAVs or human drivers, just to follow these smooth trajectory patterns. And then the following human-driven vehicles can receive similar benefits from trajectory smoothing, right? And of course, on the right figure, as the penetration rate increases, the benefit will be even higher. The benefit will be even higher. But it's exciting to see that actually we don't need a very high percentage of CAVs to achieve good benefits for smoothing. The previous studies I mentioned were about freeway was about signalized intersection trajectory smoothing. But the same concept can be actually generalized to freeway operations. For example, speed harmonization at a bottleneck. Let's just consider a problem such as the figure on the left illustrates. So we basically look at the freeway lane segment, and there is a bottleneck, either reduce lane width or cut down of a lane or an on-ramp or any kind of bottleneck. And then if this bottleneck activates, actually the vehicle trajectories will have slowed down and a queue will start to form. And the idea of this study on freeway speed harmonization is actually using the similar CAV smoothing technique as this red curve highlights. So we want to have, guide the CAVs to hedge against the stop and go waves produced by the bottleneck and try to slow down a little bit and exit the bottleneck at the right time, just to to be enough to meet the traffic when the traffic has already recovered from the bottleneck slowdown. And this problem has some fundamental similarity with the arterial, signalized arterial control. Because the bottleneck is just slowing down the traffic. And it has a similar impact as signalized. It creates a queue, and then queue is going to dissipate. And if we get this commonality between these two problems, we can use similar ideas to smooth the vehicle trajectory. So basically, we in this particular problem, we actually assume that we have some sensor measures from the upstream and downstream of this bottleneck, and we may also have some probed vehicles, like connected vehicles, and around this bottleneck, and we can synthesize the connected vehicles and sensor data to do some prediction about the downstream traffic state, such as here the step 1 prediction problem investigates. And after predicting the downstream traffic, in particular the trajectory right in front of this CAV trajectory, that is a PT here, that blue, this blue curve right in front of the red curve. After we predict that, then we're going to use in the shooting heuristic, that's what we proposed earlier, to design the CAV trajectory and let it just to be smooth enough and hedge against this stop and go waves. So that's a basic principle. So, and next we also investigate some interesting problems about joint trajectory and the signal optimization. So earlier studies, we actually assumed that the signal timing is given, but now we actually can jointly optimize the signal timing. We assume it's variable and adjustable, and its timing can be coordinated with signal trajectories, with CAV trajectories. So this way, the traffic performance can be further improved as opposed to signal optimization or trajectory optimization alone. And we actually applied this to some numerical studies, and we found that significant improvements can be made at the signalized intersection. And we can also actually adapt this idea to the control of a work zone. So basically the work zone is just like elongated signal intersection with just a longer clearance time, and we can still use the same principle to do the trajectory optimization. And recently, actually, previous studies actually used some prescribed the formulas to design a vehicle trajectories, and one place where we can improve is to improve their adaptivity and flexibility to the human-driven vehicles around the CAVs. Actually, we particularly are interested in mixed traffic, and so we actually recently did some work using deep neural networks and learning techniques to design a vehicle trajectories. And this learning technique, the advantage of this learning technique is actually can take in real-time information very effectively and have the autonomous vehicle control adaptive to real-time traffic states. And we don't need to constrain a vehicle trajectory in a certain formula or certain shape, and the learning will give you the best shape. So this is something in our work. And so basically this gives you a brief introduction about my line of research on the trajectory control and how to use this concept to improve traffic operations. And next, I want to go from the microscopic perspective to the macroscopic issues. So actually we've seen a bunch of trajectory optimizations, and what is the implication of the trajectory optimization to the higher, if you look at the problem from a 10,000-foot view. And I think essentially these trajectory controls will determine the headways between CAVs and between a CAV and a human-driven vehicle. So basically the headway is probably the most important factor that links microscopic trajectory operations and a macroscopic capacity analysis. Actually, we really, the most critical issue in capacity analysis is that for mixed traffic, because that's actually the problem we want to address in the near future when CAV fleets arrive. So I have to highlight that so what are the fundamental difference between CAV traffic and human-driven traffic from the perspective of capacity? I think there is one outstanding difference is actually for CAV traffic, you have to consider heterogeneous headways in the mixed traffic. For example, if we see a red vehicle CAV and blue vehicle human-driven vehicle or HV, and we need to consider 4 headway types. HV following HV, CAV following CAV, CAV following HV, HV following CAV. And these 4 types of headways have different characteristics and distributions. And we did some literature review, and we found that these headways actually are pretty scattered within each category and have significant differences across different types. Right? And one issue, and lots of studies just optimistically assume that CAV following CAV has a minimum headway. But I just wonder whether this is always the case. I mean, are we a little bit too optimistic? You may want to ask this kind of question. Let's look at what happened, actually. This is probably a piece of news you might see before. Google car was pulled over being too slow and driving too conservatively. So that means probably keeping a too long headway from the preceding vehicle. And also, if you test the ACC vehicles, and if you activate, adaptive cruise control. If you activate if your vehicle has adaptive cruise control, if you're activating and using it on freeway, you're going to see lots of times your headway from the preceding vehicle is a lot longer than other vehicles' headways. Other vehicles are human-driven vehicles. Actually, if you look at freeway traffic, some human-driven vehicles are pretty aggressive. They can follow the preceding vehicle with like less than 1 second headway, right? So this is not always the case, I guess, that the CAV is always better than human HVs in terms of headways. At least in the near future, when these technologies are just to put into market, we have to pay attention to this issue. So in some, let's say, pessimistic technology scenarios, we may see CAV peers may keep even longer headways as opposed to, compared with HV following HV. So in this study, we have to consider the different technology scenarios and really fully realize the uncertainties of the technologies when we analyze the capacities and talk about planning issues in like 10 years or 20 years ahead. So besides the heterogeneous headways, actually another important issue is the spatial distributions of these different vehicle types. So there is going to be 2 factors that largely determine the spatial distribution of these vehicles. First is the market penetration rate. You all know market penetration rate, right? That's a percentage of CAVs over the total number of the vehicles. If the technology is optimistic, of course, the higher CAV market penetration rates will improve the traffic capacity, like this bottom figure shows. And another factor that is not very well investigated and is also a focus of our study is actually platooning. I call it platooning intensity. If you look at these 2 figures with the same market penetration rate. But I organized the CAVs in longer platoons in the bottom figure. And if the CAV platooning indeed can bring in headway savings, actually the lower figure will give you a higher CAV capacity because CAVs are platooned with other CAVs. You see CAVs are clustered into long platoons. So they form like kind of CAV trains. That's going to further improve the capacity if the technology is optimistic. All right, so these two factors we have to consider that. And we built a very simple model to capture heterogeneous headways as well as these two features, market penetration rate and platoon intensity for mixed CAV traffic. And so basically we look at the different pairs and assign a different transition probability. I'm going to skip the technical detail. But with this nice model, we actually used just a very few number of parameters to quantify these complex problems and really quantify all these features we mentioned before. And we come up with an analytical capacity model for CAV mixed traffic capacity, and we want to make it very simple and easy to use in practice. So we made some approximation to further reduce its complexity. Of course, we did a bunch of theoretical analysis to show that this approximation is reliable and accurate in real-world applications. And we conducted a number of numerical analysis to show, how these different features like penetration ratio, P1 as P1 shows in these two figures, and the platooning intensity as O shows in the legend, how these factors will impact the high mixed traffic capacity. And we investigate different technology scenarios, like the left is optimistic headway scenario, the right is a conservative headway scenario. And under that, we see both market penetration rates and the platooning intensity will improve the capacity. The capacity is actually vertical axis. But on the right, if the technology is conservative, this might not be the case. There is going to be some pivoting point, and after which, higher market penetration will instead reduce the capacity or throughput. So what's the application of this work? I mean, it's just like the fundamental of traffic operations. And when you talk about capacity, it's probably a notion that every study needs to use, in particular for planning and also for some real-time management. One example is land management. Some people propose to use dedicated CAV lands, as illustrated in this figure. We can assign some lands that are exclusive to CAVs, and because if they have platooning advantages, maybe it's good to allocate some exclusive lands to have them being fully platooned, which maximize the CAV throughput, right? We propose the model to determine the optimal number of CAV lands versus the remaining mixed lands at different traffic conditions with different traffic characteristics, including the demand rate, the platooning rate, the platooning patterns and market penetrations, and so on and so forth. And we can solve this problem very easily with some existing techniques for integer programming and or even enumeration. And we found that this study actually yields pretty practical and useful tools to simply determine the optimal number of lands. We actually came up with some simple formulas to help engineers to determine the optimal number of the CAV lands, and based on the traffic characteristics. So, and we can see, so these things are actually very important for traffic planning. If you're a transportation system planner, and I mean, these things are just like input to any kind of your planning models. like capacity formulations and the lane management formulations, and also for operators, right? In the future, when the CAV vehicles indeed arrive, and we may need to use some of these tools to determine how to regulate them. For this capacity analysis, we can determine the number of the managed lanes, and for previous trajectory optimization, we can think about how to guide these CAVs to improve the traffic performance, right? These are basically lots of the theoretical studies and simulations and things happening on computer, and we know only with this kind of this level of work, and it is not sufficient to really deliver that full concept and convince that public that this is the way to go. We have to use field experiments to demonstrate some of this work. Although this is probably not the most technical challenging part, but I think still it's good to close the loop, to start from the paper, but let's end up with field. So we actually started a number of field experiments. Let's first talk about the pure CAV studies. Actually, a couple of years ago, I worked with the partner institute, and with if we can play videos here, it'll be great. Stephanie, if we can play the video. Oh, yeah, great. So basically, we put 15 vehicles to test on the public road. These are all human-driven vehicles. We have furnished them with high-resolution CAVs, and with high-resolution GPS devices, so we can track their trajectories. So with their trajectories, we can analyze their driving behaviors, and that gives the answers to the how HV follow HV and their headways and how they respond to stop-and-go traffic, right? And another thing I want to mention is, let's turn to next slide. We actually just put through a patent on a video recognition tool we developed to actually extract the vehicle trajectories from the drone videos. You know, right now, actually, drone technologies are becoming more and more popular, and it's pretty cheap to fly a drone to capture the vehicle images in a good angle. We can use video processing to extract the vehicle locations, and we developed some sophisticated algorithms to automatically identify the lane and extract the trajectory and extract all the performance measures, such as headway, speed, flow rate, throughput, and acceleration, this kind of thing. Once you have trajectories and lane numbers, you pretty much have everything. So we just put through a provisional patent on this development, and we're using them in a couple of the proposals to analyze the human-driven vehicle trajectories. And here's another example, next slide, of the use of this tool on a roundabout analysis. Basically, we can not only for the freeways, we can look at complex intersections, and we extract the vehicle trajectories, and using our smart lane matching algorithms, we can put them into different lanes, and we can come up with, if you look at right, we can look at the right figures, we can come up with this space-time trajectories, and we can basically archive the video development into structured flat file, including with very high resolution. So these kind of tools are very important for extracting trajectory and data to understand what's going on with the human-driven traffic. Next, we actually, I presented the speed harmonization in one slide. You may still have some impression. Actually, that was not just in theory, actually. It was a funded study from Turner Fairbank Highway Research Center, and they have 5 level 1 Cadillac, and we actually implemented part of the algorithm with their Cadillac and put together some test on the speed harmonization with their automated vehicles.
Down to 25.
Next, the previous studies mainly focus on either pure vehicles or HVs or pure CAVs controls. We also currently initiated some collaborations with Institute, and they have a state-of-the-art 2.4 kilometer test track, and they have an up-to-date and connected vehicle communication infrastructure and different CAV and a fleet of CAV vehicles. And currently, we started some experiment on the mixed vehicles. So, in this experiment, let's say, in this experiment we have just finished. We actually asked the HV to follow a CAV. This doesn't work. We may need to share the screen. Let's see. I'm going to share the screen. Yeah, if you can see. So basically, for the studies, we want to investigate the interaction between a CAV and HV. So the important question is how a human-driven vehicle or HV follows a CAV. So in this experiment, if you can see my screen now, the first vehicle here is a CAV, which is equipped with state-of-the-art LiDAR and all kinds of algorithms. This is level 2, and it's not only longitudinal but also latitudinal. And the following vehicle is actually a HV driven by a human driver. So the preceding vehicle, the first vehicle, can be switched. Let's play the video, and you're going to see the preceding vehicle. There is even no driver. So I think this is just to show that the advantage of this vehicle. But actually, in real experiment, we put the driver there. So the first vehicle can be switched between HV or AV, and we're going to see how the following vehicles' driving behavior changes when the first vehicle switches from CAV to HV. And you can basically see these two vehicles are just following each other on the straight road, or on this test track. And in our experiment, we just cut the following behavior on the straight segment, not the curved road segment, just to exclude other factors. So let's go back to the slide. Let me see. Okay. Yeah, and then we did some analysis about the results, and we tested the difference between HV following CAV and HV following HV, and we plot out a number of interesting measures, such as falling gap over the driving speed and falling headway over the driving speed. The red points are the red markers are actually for HV following CAV and or AV. The blue ones are actually HV following HV. We see, interestingly, drivers have different behaviors. Some are like tech-phobic, like those left, the driver 1 on the left. You're going to see these keep even longer distance and longer highways from following CVs compared with from following HVs. But some other drivers, seems like are tech pro, and they want to follow the CAVs closer because they trust technology, or they feel like following a CAV probably feels more comfortable because CAV drives more stably, right? So these are actually the things we have done, and we actually still are continuing on lots of these experiments. We want to really implement most of our proposed studies and algorithms that we introduced before in this presentation to this tested field. And we're currently conducting some experiment on lane changes, and then next we're going to conduct some experiments by coordinating traffic signals with the CAV trajectories in a mixed traffic flow. So with this, I conclude today's presentation. I guess there is some there is a few minutes for the questions and answers. And before that, I would like to I would like to acknowledge all the students and collaborators and also funding agencies that make these studies possible. And finally, I thank you all for your patience and for dialing in, and I'm happy to answer any questions if you have.
Okay. Thank you, Shaw, so much for the great presentation. And I do, again, apologize for those that were here at the beginning and we had some technical challenges. I know those that you were listening to the recording don't know what happened, but again, thank you so much. So just as a quick reminder, that Q&A box is located in the bottom right-hand corner of your screen. Simply type in your question and or comment. And we'll get to any questions that you have. I do know some people have stepped away, but if you could take a few, what I'm going to do as we start with these Q&As, I'm going to open up the evaluation on your screen. If you could take a few moments to complete that evaluation, as the feedback provided is very important to not only the webinar series, but to Dr. Lee as well. So the first comment I have came in, and maybe you could add a little bit of insights as well. The fuel efficiency can be improved with CAVs due to the smooth trajectories in signalized environments. Most CAVs typically operate in a very conservative manner to maximize safety with increased headways and decreased speed, which seems it would reduce throughout rather than increase throughput, at least with heterogeneous fleets that are not fully autonomous.
Thank for this question, and I guess this is a comment, right? I guess.
Yes, more of a comment, but I didn't know if you wanted to provide any additional feedback on that comment.
Yeah, I completely agree with this comment, and the traffic smoothing will definitely improve the fuel efficiency, and the conservative driving behavior of the CAVs, at least in the first stage of this technology, will likely reduce the throughput. But I just want to comment on these two issues. Throughput and the fuel efficiency can be separated, even if the conservativeness or safety margin decrease the throughput. You can still realize the traffic smoothing to harvest the benefit from fuel consumption, because even if you keep a longer headway, but you can still drive smoother and adjust your trajectories more coordinated with the signals, and that's going to give you extra benefit in fuel consumption. And that can possibly offset some of this drop in throughput or capacity. So that's basically my view, but I completely agree with this. So like the next question is coming.
Yeah, it says, how are pedestrians and bicyclists accounted for, I guess, accommodated?
How are pedestrians and bicycles accommodated? Yes, this is a good question. I guess, in order to comprehensively address this question, we probably need to talk to some experts from Qatar, investigating more pedestrians and bicycles. So basically, I think they need to be, so the highway, in my view, if there's always going to be a trade-off between the system efficiency and the freedom of personal use. So it's if we really want to realize that benefits of CAVs, we might want to try to set up some physical separations between CAV traffic and pedestrian bicycle traffic. And that's also not only for CAV traffic, actually. It's pretty urgent for the existing traffic. I myself, I'm not comfortable riding a bicycle sharing the rights of way with current human-driven vehicles. And I think in some other countries, this is pretty well managed when the pedestrians or bicycle volumes are pretty high. And I think when pedestrians cross the street, they have overpasses, and bicycles, they have like dedicated lanes separated from the main traffic. If we get to a certain volume, we can definitely do that. But if the volume is high, these options are not economically viable. We have to do some analysis to see whether we're going to sacrifice the CAV's efficiency to accommodate the safety requirements mixed with pedestrians and bicycles. And also, I think connected vehicle technologies will play a big role. I mean, in our pilot project here, I heard that lots of initiatives of warning the CAVs and of the presence of pedestrians with bicycles using connected vehicle technology. That may also help mitigate the risk. And
okay. Okay.
yeah.
We have one. We'll take one more question. I know we had to start over at the beginning, so we'll just take one more question. And it says, how does the CAVs get prepared or react to an accident or weather event?
Yeah, all right. I don't see that in this box. So how does, okay, the weather event. All right. So, the weather event is some technologies. So as of now, I think, the weather events are, CAVs are not fully mature. But even for human drivers, we don't react very well when we driving the inclement weather conditions. I was from Illinois, and when there was a snowfall, I drove on freeways. I saw lots of vehicles pulled off from the road, and they drove too fast or something like that. So this is definitely the challenge. But the issue is, how we're going to mitigate this kind of risks against the weather. If the CAVs can do no worse than human drivers in the inclement weather, I don't know whether we want to put a little bit mercy for the technologies, or we have to wait until everything is 100% reliable to put it on market. I mean, some of the issues goes beyond the engineering technologies, but I think there are 2 points. First, the technologies develops, definitely these kind of issues will be better and better. But second, we need to greatly weigh the risk of CAVs against the weather versus humans against the weather. Of course, the first deployment of the CAVs and some of the fleet are actually, some companies intentionally pick the spots in southern cities, like I don't know, Phoenix, or even some companies thinking about Tampa, just to get around the weather issue. So that issue needs to be addressed in the future. But I don't have a clear answer of that. Some of the vehicle technologies, but I have a good hope for that.
Well, thank you so much, Shaw, for the great presentation today. We do have another webinar scheduled for this coming Tuesday. It's not on our normal rotation, but we wanted to fit in this topic, talking about Star Metro, which is up in Tallahassee, Florida. They piloted a mobile fare payment app, and that will be presented by 2 of our researchers here, Sarah Hendricks and Dr. Sean Barbeau, and then Kelly Robertson from Bow Stern. So again, thank you so much for attending today's webcast.